All right. So let's move on to the next model, regularized logistic regression. Because we have learned the concept of variance bias trade-off, and we also have sort of have an idea of regularization. So everything will be kind of straightforward. So we first prepare the data and split the data, and then let's take a look at logistic regression model as a review. I know some of you have learned this model before in previous classes. Let's just briefly review it. So a logistic regression is to predict y using a bunch of x variables, where y is binary. By default, y is a binary variable with only two classes, right? Suppose y is equal to 1 with probability p and 0 with probability 1 minus p. If we define it. And the goal of a logistic regression model is to use a function of x variables to predict y. Right? So this function may not be a linear function. We cannot use a linear function actually because y only has two distinct possible values, 1 and 0. Right? It's not a continuous, it's not on a continuous, it's not a continuous variable. It is discrete variable, right, with only two possible values. So you can imagine if you use a linear regression model, for example, like this, then when you do prediction, the predicted value is not bounded, right? And the values are continuous, so they don't match. So that's why we cannot directly use a linear model to predict y if y is a binary variable. And so in fact, a logistic regression model estimates or predicts the probability of y equals 1. And so the focus is on predicting p, the little p, which is bounded by 0 and 1. And for prediction of y, we will just round p hat to either 0 or 1. So we try to use this build a model to predict p, so that we can calculate p hat given a new observation, then round it to 1 or 0. If it is greater than or equal to 2.5, y hat is 1, otherwise 0. Right? So to construct the model, we first define an intermediate predictor z as a function of the x variables. So this is like our regular multiple linear regression model, z. And since p is between 0 and 1, we cannot use z to predict p directly using ordinary linear regression. So instead, we figure out a way to connect them together. Notice that p over 1 minus p, which is called the odds of this random event. So this is defined on the positive real line, right, from 0 to infinity. If p is 0, it is equal to 0. If p is 1, it is equal to infinity. Right? The odds is defined on this positive real line. Right? And then the log of odds, consequently, will be defined on the entire real line. From negative infinity to infinity. It is not bounded. Consequently, we can use this linear predictor to predict log odds directly. And if we solve for p, e to the z, right? And then furthermore, if you solve for p itself, it would be equal to, it could be like this. And this z value, the z is this linear predictor. Right? So the entire model fitting is like this. We try to optimize the model or find the best set of estimators of data so that the overall likelihood is maximized. And after we find those parameter estimates, like beta 0, beta 1 hats, all of these beta hats, okay, how to do prediction? We plug into this formula and multiply it by the x values and calculate p hat. And lastly, we round p hat to 1 or 0. It is using the majority. If it's greater than 0.5, then 1, otherwise 0. So this function is called the logit function. Logit function is this S-shaped function. You see it's the support is from -infinity to infinity, and it's S-shaped. And the y values, the function values are bounded by 0 and 1. So it's perfect for predicting a probability value, p value, the value of p. All right, so this is how we do construct a model and do prediction. From this, for a new observation, the linear predictor is like this, and p hat is equal to this, and then round it. Okay, so this is the whole thing about logistic regression. And then let's fit a simple logistic regression model. Now we will consider 3 variables: AF prop, region, and this one. Okay, 3 variables using this formula. Oh, by the way, we will use this package, GLMNET. So this package includes generalized linear models, and also including logistic regression models, and also cross-validation functions. And so we can actually use the building function to do cross-validation very easily. We don't need to split the data to like 5-fold and run the model again by ourselves. There is a building function for that. Okay. So let's load the package, specify the formula, and then we need to prepare the data first. So all of the X matrix that can be accepted by this function should be a matrix like this. Okay. So namely, all of the categorical variables must be transformed to dummy variables, and this function will automatically do so for us. Okay. We just need to feed the formula into it and specify the data set. Okay. So it will find the variables in the formula in the data set we provided and create dummy variables for all categorical variables. For example, the region, this region variable is a categorical variable with 4 levels, 4 categories, right? Like south, north, west, etc. Midwest, etc. 4 regions. For each variable, it will create a dummy variable. So anyway, this will prepare the data for GLMNET. Then we can feed that. So this predictors is the X matrix. It only contains X values, including those dummy variables. Okay? And then specify the Y variable, which is the winner. And family equals binomial. So this is for logistic regression. If you are doing a logistic regression, we need to specify it like this. And lambda, this is a tuning parameter for regularized logistic regression. Let it be 0 now, without any regularization. We just feed a standard logistic regression model. And this standardized equals true. So this one is used to this argument is used to specify whether or not we want to standardize the feature variables. By default, it's true. I listed here because actually the model pre-processed the data before doing the fitting. So this is, it will standardize the X variables first. And then after we run this, we see the result here. We can pull out the coefficients, intercept, and also slopes, right? And we're done, right? So this is the initial fitting of a logistic regression model. Big one. And let's create a new function to calculate the misclassification rate for logistic regression model. The reason that we need to create a new function is because, remember, whenever we feed any data matrix into GLM-NET, we have to first pre-process data using model.matrix function, right? So the previous misclass function and confusion matrix function won't work directly, right? So we need a new function. So this function takes a few arguments, the data set, y. Of course, these two are like one-to-one corresponding, right? X matrix and Y vector, and fit. This is the model you use to do prediction and ultimately calculate the misclassification rate. This is the model object. And lastly, the formula. Let's see how to do it. So take the data set and fit using the model fit to do prediction on the data set. Data is equal to data set using this formula. So this one will prepare the data. And we use the predict function to predict a Y label, call it predict dot logistic and type equals class. So add a new column to data sets. And then mutate, add a new variable misclassified. So this one will return a true or a 1 or 0 values, right? Compare the true value with the predicted value. And remember this true value, this Y is actually is provided by the user, right? The true Y labels. Then lastly, calculate the misclassification rate, which is the mean of that column. All right, so it's equal to 29.22. So the misclassification rate for our initial logistic regression model is very big. Okay, it's about 30%. It's much worse than the decision tree or the random forest model. However, we don't need to worry yet because you see we only used 3 variables so far. But the previous decision tree and random forest used a lot of variables, almost all of the variables. So it's not a fair comparison yet. And then let's move on to regularized logistic regression. So far, the logistic regression model we talked about is the ordinary logistic regression model. So in this case, the model tries to maximize the log likelihood of observing the data points. Log likelihood. If you are not familiar with this, it's okay. You can just consider it's not a loss function, it's a likelihood function. For likelihood function, we always try to maximize. So the ordinary logistic regression model tries to find data heads so that the overall log likelihood is maximized. However, if you keep adding new terms to the model, the log likelihood can only increase. However, it may not be a very good idea because if you keep making the model more and more complex, the variance of the model will increase quickly, right? And the bias will decrease. But it may not be the optimal choice, right, to have a very complex model. So the regularized logistic regression model will try to balance the two terms, variance and bias. Right? So it actually will minus a penalty term, which is used to control the size of your model. If we use L1 penalty, the penalty term will be lambda times summation. Yeah, it's this one. Lambda times summation beta, the absolute value of beta j. Right? So this part apparently control is a measure of the size of the model. Right? The more variables you have, the more betas you have, this quantity must be bigger. Right? And also at the same time, the bigger the magnitude of each beta j, the bigger the absolute value of it, and consequently the bigger of this, right? So overall, this term controls is a measure of the size of the model. And lambda is a tuning parameter. We can tune this value to adjust the penalty, how harsh the penalty will be. The goal is to maximize the likelihood. However, if you keep adding terms, this will be bigger too, right? So it will offset the increase in the likelihood. So this will increase at the same time. Anyway, let's see what else. So ordinary logistic regression minimizes the bias only, but the regularized logistic regression introduces the bias to the model in hoping for minimizing the total precision error. So this part will introduce bias. Let's see how to tune it. So before we tune it, we can just blindly let it be a small constant, for example, 0.05, and see the result. So see by letting lambda equals a small positive value, some of the coefficient estimates are missing. That means they are gone. They are gone. They are removed because they are not useful. Right? I mean, not useful anymore. Right? So this actually shrinked the model to a smaller one. And the package has this function called cv.glm net. So this function can help us to use cross-validation to tune the lambda, the value of lambda. It's very easy to use. Just provide the X matrix, the Y vector, and specify the number of folds in the cross-validation, specify the family type, standardize. So this is the default option, right? This is the default. You don't have to specify it, right? And then we can plot the result. So this one has a lot of information, the different components, right? But if you plot it, you will see this kind of plot. Right? So the x-axis is corresponding to log of lambda. Remember, lambda values are very small positive values. So if you use a plot to show their original values, they will be very small and clustered together. Right? So we will just take a log of them to enlarge the magnitude of them. Right? So that's why they are all negative, because all of the lambda values are small positive values. Usually lambda is smaller than 0, smaller than 1, greater than 0. So log lambda is negative, true. But it's still a monotone function. When lambda increases, log lambda also increases. Right? So that's why from this to that direction, the penalty is harsher and harsher. Okay, the tuning parameter is bigger and bigger. Okay. All right. Now the y-axis is corresponding to misclassification rate. So as you see, when lambda increases, Okay, so this is the minimum. Oops. So this is the minimum log lambda value. Okay. And the second one, so this one has even a larger lambda value. However, you see the misclassification rate is within one standard error of the previous one, the minimum. Okay. The next one is not. So this value is not in the one standard deviation of the minimum anymore. Right? So consequently, so this lambda is the optimal choice if we use the parsimonious way, right? One standard error rule, right? And the previous one, so basically these two will be both printed. Right? And let's see the penalty. So this function actually use an elastic penalty. So it's a combination of L2 norm and L1 norm of the beta coefficients. So it's called elastic net penalty. So instead of this one uses L1 penalty, L1 penalty. But the function we see this one actually use this elastic penalty. And then actually in the output, there's these many terms. You can choose to print them out or extract them. If you print the fitting result, you'll see this. In particular, you see the two lambda values are listed here in the table. The first one is the lambda value that will minimize the misclassification rate. And the second is the lambda value with the misclassification rate within the one standard error of the minimum. So it really depends on which one you like. They are slightly different because our formula is very simple. We only have three variables, right? And we can take a look at the optimal model if we use lambda 1 SE. And yeah, what if we use the full formula? To do a fair comparison, we should consider all of the variables that we use in the decision tree model and the random forest model, right? Because we have this penalty term available in the system, we're not worried, right? No matter how many terms are included in the formula, we should be good because the regularization process will automatically push unnecessary terms to zero, for the coefficient to be missing. Right? So let's do this again. Run this cross-validation again. Probably fit 2. So this is the result. So in this case, you see lambda min and lambda 1 and C are quite different. Okay, and also the number of variables are also very, very different. Okay, if you use 1IC, only 30 columns, well, 30 variables will be kept. But if you use minimum misclassification rate, there'll be 89 columns. Yeah. And you might wonder why there are so many variables. We only have about 23 variables, right? Why there are so many? Remember, that's because we use this model.matrix function to transform our X matrix. Namely, all of the categorical variables will be transformed to dummy variables. Right? So if a categorical variable has C categories, it will create C columns and C dummy variables. Right? So it will dramatically expand the data matrix. So that's why you see these many variables. All right. So this is the performance of the optimal model. It's actually pretty good. Is similar to the misclassification rate of the optimal model of random forest. Actually, it's about 17%.